Welcome back to Integral Calculus. In this video, I want to look through the process called partial fraction decomposition. In theory, this is something that you've seen before. Every college algebra textbook includes a section teaching partial fraction decomposition. In practice, I have never in my life seen an algebra class that has enough time to actually include it, so it gets skipped over and it's just a waste of pages. I'm going to treat this as though you've never seen it before, but this video is just going to be all about the algebra and not at all any calculus. We'll do the calculus involving it in a future video. I'm also going to be very kind to you. And assume that we have a fraction where the denominator is already factored. It turns out that when you have a fraction like this, it is always going to be possible to decompose the fraction into a sum of simpler fractions, where each factor from the denominator is on its own the denominator of one of the simpler fractions. In the numerator, we will have something simpler still. In this case, our denominators are both linear, so the numerators have to be simpler than that, and they're going to be constants. I just realized I've gotten a little bit ahead of myself. Even though this is factored, you should notice that in the original fraction, the denominator is quadratic, while the numerator is linear. The degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. That is necessary. If you don't have that, you can't do partial fraction decomposition. But we do have that, so we can happily do partial fraction decomposition. And at this point, we have an equation. Our equation has fractions in it. I hate having fractions in an equation, so I'm going to multiply both sides of the equation by the common denominator. One of the nice things about partial fraction decomposition is that the common denominator is always the denominator of the fraction on the left-hand side of the equation. Always, without fail. Because we designed the right-hand side of the equation so that that would be the case. So we multiply 5 minus 2x over x minus 1 times x plus 2. We multiply it times x minus 1 times x plus 2, and the x minus 1's cancel out and the x plus 2's cancel out, and we're left with 5 minus 2x. We take a over x minus 1. We multiply by x minus 1 times x plus 2. The x minus 1's cancel each other out. We're left with x plus 2. And likewise, on b's, the x plus 2's cancel out, and we're left with x minus 1. Doing a little bit of rearranging. And I can write negative 2x plus 5 equals a plus b times x plus 2a minus b. And here we get to the next key idea in partial fraction decomposition. The first one just being that we can do this. We have here two polynomials. And usually in algebra, you're looking for a particular value of x that satisfies a polynomial equation, something you can plug in and get a true value. That's not what we want here. We want something a little bit more. We want that no matter what value of x we plug in, that this equation comes out to be true. It turns out, if anyone goes on to study linear algebra, you will learn why this is the case in that course. But it turns out that the only way for this to work out is for every set of coefficients to match up. The polynomials have to be the exact same polynomial. So our polynomials on x, or our coefficients on x, on the left-hand side, that's -2. On the right-hand side, that's a plus b. And our constants, I usually use the number 1 to represent constants in this context. On the left-hand side, that's 5. On the right-hand side, that's 2a minus b. This is a system of two equations in two unknowns. This particular system is relatively easy to solve because I notice that if I just add the two lines together, well, I'll get 3 on the left-hand side, I'll get a plus 2a, which is 3a, and I'll get b minus b, which cancel each other out. So 1 is my value of a, and plugging that back in gives me that -3 is the value of b. If you still have this visible, then you can jump right ahead. I don't, so I'm going to copy down. There we go. I'm going to copy down that expression before plugging in 1 over x minus 1 plus -3 over x plus 2. And that is the simplified or the decomposed version of the same rational. If you want, we can double check. We can find common denominators. We can distribute and add together and verify that we do in fact get the thing we started with. All right. Same thing, just a little bit bigger. X cubed plus 9x squared plus 17x plus 7 all over x plus 1 squared times x squared plus 2x plus 3. The two things that can happen that make partial fraction decomposition a little bit more challenging both appear in this denominator. First of all, I have x squared plus 2x plus 3. This is a quadratic polynomial that cannot factor any further. Every polynomial can factor down to linear and quadratic factors, but not every quadratic factor can factor down into linear factors. That's going to be an annoyance. It makes the process harder, but it's a thing that can happen and it's a thing we will be able to deal with. The other factor, x plus 1, is a repeated factor. The fact that it's repeated also makes things a little bit more complicated. So to deal with these things, those are still going to be the only denominators we get, we're going to have x plus 1, the whole thing squared. We're going to have x squared plus 2x plus 3. In this case, both of our denominators are quadratic. 1 degree simpler than quadratic is linear. So instead of an arbitrary constant term in the numerator, we're going to have an arbitrary linear expression, ax plus b and cx plus d. Everything is going to be messier as a result of this, but the process is going to be identical. Multiply both sides of the equation by the common denominator. On the left-hand side, everything cancels out with the denominator. On the right-hand side, one factor cancels out with the denominator. Distribute, cleaning up on the right-hand side. Keep distributing. And then regroup with all of our like terms together. Trick that I learned long ago, whenever you're dealing with an ugly polynomial like this with just so many terms all over the place, underline things as you use them to make sure you don't lose anything and you don't double anything. I like to use a different form of underline in every grouping so that I can better keep track of what's going on. Right. And then I'll double check by counting. I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms in the earlier line. And if I count the stuff in parentheses, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things. So I probably didn't lose any. Now that I have done that, I can build out my system of equations. My x cubed terms. On the left-hand side, the coefficient of x cubed is 1. On the right-hand side, the coefficient of x cubed is a plus c. My x squared terms. I've got 9 equals 2a plus b plus 2c plus d. My linear terms, I've got 17 equals 3a plus 2b plus c plus 2d. And my constant terms, I've got 7 equals 3b plus d. All right. System of 4 equations in 4 unknowns is annoying, but we know how to do it. We know how to deal with this. eliminate one variable at a time. I think I'm going to start with D. And one of the reasons I want to start with D is because, well, the first one's already done. 1 equals A plus C. Then take these two equations and subtract them. I get that 2 is equal to 2a minus 2b plus 2c. And why not divide by 2? 1 equals a minus b plus c. And I'm really getting somewhere at this point, because I can subtract those two equations. That gives me 0 equals b. That is incredibly convenient. B is 0. All of my b's are gone. To make things particularly convenient, look at what that did to this last equation. 7 equals D. All right. So let's rewrite our equations with that information. I've still got the equation 1 equals A plus C. Not really much I can do with that. I've got 9 equals 2A plus B, which is 0, plus 2C plus D, which is 7. And I realize that that second equation is just the same as the first equation. I don't have any new information there. I can get rid of that equation. Then the third equation, 17 equals 3a plus 2b, but b is 0, plus c plus 2d. 2 times 7 is 14. Subtract 14 from both sides of the equation, and I get that 3 is equal to 3a plus c. Now I'm down to 2 equations in just A and C. Let's subtract these. Just take the negative of that first equation, gives me 2 equals 2a, which means that the value of a must be 1, and if I plug that back in, 1 equals 1 plus c, which means that c is also 0. All right, so a is 1, b is 0, c is 0, d is 7, and if I scroll back all the way to the beginning, I set this up with this fraction in mind. Plugging in all the values I just came up with, I have now successfully decomposed this fraction as much as I'm going to be able to. And we can all take a sigh of relief because we finished. Partial fraction decomposition quickly becomes incredibly tedious because it's solving systems of equations. Right? Systems in 2 variables are easy. Systems of 3 variables make you want to tear your hair out. Systems in 4 variables make you want to curl up in a ball and cry. And, well, it gets worse from there. Luckily, computers are incredibly good at systems. Solving a system of equations using computer software is the thing that a computer is best at as far as computation goes. So for our purposes in this course, we're going to look by and large at very simple systems of equations. And if we don't have the luxury of doing that, we're going to look at set up the system and stop there because a computer can handle the rest. Here's one for you to try, and it is a little bit more challenging than the ones I've been going through. X squared plus 2x plus 3 over x cubed minus x. Because in this one, I did not give you a denominator that was already factored. You're going to have to take the time to factor that denominator and then go from there. Take a couple of minutes, see what you can do with that, and I'll see you in the next video.